stack them all in a 3D plot as such. This is what defines your random process. Instead, you'll receive something like, let's say this, okay? So if I go ahead and repeat this, you see all those guys, all of them define different trials. Each time I run this code, I get a different the integration over the squared part. Hey guys, welcome to lecture 12 of this course entitled Signal Processing, where in this one, we'll be talking about random processes and why do we need random processes in signal processing. We're going to start by defining a basic communication system, and from there, decompose the received signal into its counterparts that are the information, interference, and noise. Define the sample space that produces or generates the different signals that define the so-called random process. And last but not least, on MATLAB, I'm going to show you how to perform different experiments or trials to generate your random process. So without further ado, let's get started. So let's say we've got a radio communication system. That is a system composed of the transmitter, denoted hereby as TX. We've got a receiver, denoted by RX, and we've got a communicating channel between the two, denoted as channel. So each one represents a block in this radio communication system. Now I'm not going to zoom in on each and every block. Indeed, the transmitter and receiver by itself is so sophisticated that I cannot buckle all the sub-blocks in one lecture. Instead, what we're going to focus on in this lecture is random processes. That is, why do we have random processes or random signals when talking about or when dealing with or when modeling received signals? That's the focus of this lecture. So we've got this radio communication system. The goal of this system is that the transmitter wants to send a sort of signal that corresponds to some information intended to the receiver. In other words, the received signal will be such that it contains some useful information, of course, sent by the transmitter. Plus, now ideally what we'd want is to receive the information as is, right? But in a real life scenario, that's nearly impossible, as no signal is sent without any deformations or distortions or these type of perturbations. So a signal is rarely received by its own, so we're going to add some unwanted interference. Could be from other transmitters transmitting in the same bandwidth of the system, plus some, background noise. Now let's talk about each and every one of those components. The information could be really any physical quantity, it's not like it's something super out of this world information, like, no. It's any physical quantity that you could think of. For example, it could be voice. Like you're talking over the phone and you're sending your voice. So the transmitter block over here is responsible about, cutting down the noise into, small bits of information so that they could be reliably sent across the channel, because the voice is not sent as is. A lot of sophisticated signal processing techniques are found within this transmitter block to encode your voice signal so that we minimize the bit error rate of the total system. And really, there's a lot of stuff going on. So this is one type of information that could be found within the information part of the received signal. Another one you could think of is text. So let's say you're sending a certain SMS to your buddy. Well, the text is also, encoded in a certain way that it could be reliably sent across the channel. You could be sending video and many more, right? Now, as for the interference block, this component typically represents some unwanted, electromagnetic waves which are produced from other communication systems that are typically operating close to this receiver right here. How can I put this arrow? So any communication system happening relatively close to this system will thus produce unwanted electromagnetic radiations close to the communication system of interest, and thus we will have some interference interfering with our desired information. And last but not least, we have some noise, which is not due to the propagating channel and not due to, interference. No, this is another part of the received signal. It's the part where the major component contributing to the noise is the so-called thermal noise. This is usually caused by, random motion of electrons and conductors and devices, typically found in the front end of the receiver. Again, I'm not going to zoom in on the receiver and show you each block by its own, but usually in most communication receivers, you've got a front end dealing with how the signal should be forwarded to other blocks so that the signal could be properly reconstructed and information could be reliably extracted. So here's the reason why we find that received signals are random in nature. However, it's not completely random. That is, if you're sending, let's say for just, sake of presentation, if you're sending a signal of, let's say this is my time axis and this is my x of t. Say it's the received signal. So let's say, just for sake of presentation, this is by no means a signal to be sent in a reliable manner. No, it's just a signal for sake of presentation. Let's say this signal is an all-one signal or a square signal as such, okay? Over a certain period or pulse width t, okay? Typically, your signal, will not be received as such. Instead, you will receive something like, let's say this, okay? This is what he actually received. So let's say the amplitude of this pulse is 1. In an ideal world where there's no interference, no noise, you could, at any given time, t, you could predict what's coming after t. So you can know what the next sample is going to be, and you can know when, this pulse is going to end, which is at time t equal t, right? However, in the presence of interference and noise, this is one instance of a transmitted signal, and thus it is impossible to precisely tell what the next signal is. Now, this might sound that, I'm going to receive a completely random signal. I'm not going to know anything about the signal. That's wrong. That's wrong to say. And the reason why is that it is possible to describe the signal in terms of the so-called statistical parameters of that signal, such as average power, for example, and the PSD, the power spectral density of the signal, as we will show further on in the coming lectures. So some parameters of the signal might tend to be constant, or not constant, you can't say constant. Some more consistent parameters to deal with are the following two: average power and PSD. Actually, if we take a look at this, at the ideal power of this signal, which is the integration over the squared part of this guy, of this shaded region, if you do the math, then you will find that the power of x is 1 over t, integration from 0 till t, of the magnitude of x of t squared, right, over time. You do the math, you arrive at something like 1 over t, x of t is constant, over 0 till t, it's 1, so 1 squared is 1, and you get t minus 0, that is 1. However, if you integrate the actual received signal, not the ideal one, the actual one, that is, you would want to consider all the following part, then it's not going to be a random, a completely random part compared to this one over here. No, it's going to be something around 1. Right? So even though samples might tend to be random, some other parameters tend to be more stable than others, if that makes sense. So if you go ahead and integrate maybe this noisy signal over here, you might get something maybe close to 1 or a bit greater than 1, 1.2. Then the next time you read another copy or sample of this signal might be 1.5, then 0.9, and so on. And that's where it's very important to define the sample space that we work in. When I said copy of the signal, I meant each time you regenerate the signal using the same information, okay? How would it look like at the receiver? Each and every one of those signals defines a point in the so-called sample space. So let's say this is a set as such, usually referred to as sample space, or S for short. Then if we go back to the previous example and we take a look at this pulse right here, actually each time it's sent over a noisy channel, you're not going to receive the exact same signal. That's what defines the sample space. And so if I generate copies of this signal, or think about it as this. You have an experiment, the simple experiment they used to give you in high school. Let's say you've got an urn with, let's say, 2 red balls, 3 green balls, and 5 yellow balls. Each time you perform an experiment, that is, let's say you're drawing 2 balls from the urn without replacement, each time you perform this experiment, you're not going to get the same exact outcome. Well, it's the same thing over here. And the random part over here is not the urn, it's the noisy channel. And the interference, of course. It's the random part of the communication system. Well, let's say I perform 3 trials, right? In the first trial, I picked this point, which actually reflects the following signal. So it's not going to be the nice looking pulse. It's going to be something around this nice looking pulse. It's going to be, let's say, something like this. And T somewhere over here. This is my pulse width. So this is the first trial of the experiment. Keeping in mind that trial in signal processing terms is each time you perform the transmission scheme, each time you look at the received signal of the same transmitted information and you say, oh, okay, let me plot this signal over time and see how it looks like. So this is the first trial. The second trial, on the other hand, might look something like this. Even though it's close, it's not the same. Right? So as you can see, both signals are not exactly the same, but if you get a kid and you tell him, oh, could you look at both signals? He's going to tell you they look alike, right? If you get anyone from the streets or anywhere, they look alike. Well, that's because they're generated using the same piece of information. If they would look very different, then either there's something wrong or you're using something super sophisticated that even a human looking at the signal will tell you, you know what, it's really hard, to figure out what's going on. But that's not the case. The case here is that all these signals are generated using the same piece of information, and that's why they look the same, but they're not the same. So this guy was the second trial. Okay, let's do one more time. Let's say the third time we got the following signal. And when I said that they look the same, but they're not the same, it means that when I come at any given time and look at the sample at each of the following 3 received signals, I'm not going to obtain the same exact value. That is right here. Let's denote it by, I don't know, sub 1 for, or subscript 1 for the trial number. So x1 of t is by no means equal to x2 of t, which in turn is by no means equal to x3 of t. They're close. Yes, I agree, but they're not exactly the same. So we can say that they're the same. So mathematically speaking, the S defines the sample space and allocates the probabilities of the events within the sample space. So if we denote S1, the first sample, S2 the second one, and S3 the third one, then we can assign to each sample point S a function of time that we plotted on the right hand side. The first trial, the second trial, the third trial, that we denoted by xi of t. So lowercase xi of t is actually uppercase x of t and s, and to be more precise, si. Okay, where t in this case was between 0 and, let's say, p, where p is the observation interval, or to be more specific, 0p defines the observation interval. So again, this guy, uppercase x, is mathematically referred to as the realization. It is one realization or sample function. So you might find both terms in references. And again, for a fixed time t, the blue cut you see over here, this blue cut right here, we can, collect all those, points called x1 of t, x2 of t, all the way down to, now I did x3 of t, but you can repeat this. You could generate multiple trials. You can go down to, let's say, xn of t. And all those guys are random variables of the same generated at time t. Remember when we said that they're not the same, but they might be close depending on the noise? And that's where the thing comes in play. So if you take a look at time t, you've got random variables generated at this instance of time. So all in all, we have an index family of random variables, which is called a random process. So you vary t, that is, you take a look at different instances of time, and you vary S, that is, you perform multiple trials. That's what defines a random process. That is, if I go ahead and take a look at the bigger picture, that is the T space over here, the S space, that is the trial space over here, and the values of X. First time could look like this, second time could look like this, and so on. So those bi indices T and S would define what is called the random process. Now, one really, nice question asked, you can go on Google, difference between random variable and a random process. You can find a lot of answers, but the best one that, what I think the best answer is that a random variable is nothing other than an outcome of a random experiment mapped onto a number. For example, going back to the earn example, each time you perform a trial, you get a different outcome, or not necessarily the same outcome. Well, each outcome defines, a realization, which is mapped onto a number, that is the probability of this event. That's the way to think of random variables. However, for random processes, it's a bit different because you've got the time factor over here. And the time is what, sort of makes random processes stand out as different. But instead of mapping it onto a number, that is the probability. So for random variables, you would map onto a certain probability. So a number, right? But instead, with random processes, you would not map onto a number. No, you would map onto a waveform. You would map onto one of those, let's say, 3 trials you see over here. So you would map onto a certain waveform of time. That's a healthy and nice way to think of an analog definition between random variables and random processes, okay? So random variables, okay, I do an experiment, I get a number. What is the number? It's the probability of this event. However, with random processes, you do an experiment, you don't get a number, you get a waveform, which is defined according to time. I just wanted to show you on MATLAB how to get a feel of random processes and this sample space, right? So let's try to, reproduce what we had in this lecture on MATLAB. What I mean by that is that I want to regenerate this pulse using this sample space. So let's generate this pulse, right? Let's say we've got some ones, say 20 ones, not 21, 20 values of ones, and then zeros, right? So let me plot X. First of all, I'm not talking about sampling rate, I'm not talking about bandwidth, nothing. No, I'm just telling you, take the signal and look at it on MATLAB. Actually, let me change the Y limits. Let's say I'm looking between 0 and 2. And this is what you get. This is your pulse, then goes down to 0, right? Okay, let me put this guy over here. Let's put some grids. Okay, so this is how the signal looks like. You can see here it's not a sharp, descending. It's not like a sharp pulse. To get a sharp one, you should increase the number of samples. Say, so that you can have something sharp. Okay, so this is ideally the pulse that I want to send, but this is by no means achievable in a real life scenario. So instead of this X, I'm going to receive a Y plus some random noise. So let's say my uppercase N is the length of my X, and I generate some Gaussian noise. So it's a vector of a 1 by n realization of this Gaussian process, and I'll plot Y instead of X. This is what we get, and as you can see, it's completely random. I know that's because the noise was too high. Try lowering the noise by multiplying, let's say, by 0.1, and there you go. You see something close to the initial signal that we had. That is the blue, pulse you see over here. So if I go ahead and repeat this, you see all those guys, all of them define different trials. Each time I run this code, I get a different curve superimposed on top of the previous ones. So all those curves you see over here correspond to the different trials within this sample space. And to get a feel of this random process 3D curve, I'm going to plot, let's say, let's say I repeat this. Okay, so let's say I've got an experiment. Say I repeat this 100 times, right? So my X is constant throughout the whole experiment, whereas my Y will vary. So I'll loop over here, say for n going from 1 till n experiments, do this, and stack it in uppercase Y. as such. Okay, so I don't need this. Now let's try to plot all this Y matrix on a 3D plot and see how it looks like. So I'll define a mesh grid. First dimension goes to time, so it's from 1 till n. Second one goes for experiments, so it's from 1 till n experiments. And the last, that's it. So I'll stack those grids and X and T, and then I'll surf X, T, Y. Run, and there you go. So those are all the 100 experiments. So 1, 2, 3, count 4, 5 till 100, and stack them all in a 3D plot as such. This is what defines your random process, is that so this dimension right here, 1 till 100, is your experiment dimension or your sample dimension. This dimension over here from 0 till 400 is your time dimension. And last but not least, the Z dimension is the values your signal takes, right? So think about it as such. So over here, you've got an arrow, and over this experiment dimension, you've got an arrow right here, and at any given time you stop and you pick the signal over here. And that's why we said that the random process generates a random signal for each trial instead of a certain number or a probability, right? So that's it for this lecture. I hope you enjoyed it. In this one, we introduced you to random processes and why this term is important when dealing with signals and signal processing. We defined the different counterparts of the received signal, that are its information, interference, and noise. We talked about why received signals are different each time you generate your received signal using the same piece of information, why it appears different each time we redo the experiment, and then we mathematically formulated the so-called sample space corresponding to a given information, and how we could, get this sense of different signals at each different trial, which led us in the end to define a random process as an analog definition to random variables and probability. We showed you how to, generate different samples of the same signal on MATLAB. Thanks for watching. If you found this lecture beneficial, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below. I'll make sure I'll get to it as soon as possible. Also consider donating to my Patreon account any amount you wish to support the channel. Thanks for watching, and I'll see you in future lectures.